So, building on the knowledge we've now acquired about the way Mantra works, let's try constructing a shader. And to do that we need to go into the shop context. First of all, a remark about constructing shaders. It's almost always easier to take one of the existing shaders from the material palette and modify it. If you lay down a shader from the materials palette and then edit it, you can do that without any danger of it changing the original material in the material palette. You create your own material here in the shop context. So before we get too far into constructing our shader, a few words about how the Vex Builder network context works. And the nodes in this context are slightly different from nodes in, say, the SOP context. One of the differences is that you have many more inputs and outputs. The things on the right-hand side of the node here are outputs, and if we zoom in we can see that the arrows point out of the node. And the things on the left side of a node are the inputs, and here we can see the arrows are pointing inwards. If we want to see the nature of the input, there are color codes to help us. It can sometimes be difficult to remember what the colors mean, but if you hover over an input you get a little help text which tells you the purpose of the input and its type. In this case this is a vector, this is a float value, and this is a BSDF. Another difference between this context and, say, SOPs is that you can have nodes which take different types of input. And let's demonstrate that. I'm going to lay down a constant. I'm going to Control-C, Control-V that, so that we have two constants. And by default these are floats, so we've got a constant float coming out. If I lay down an add node, which, as you'd expect, allows you to add two quantities together, we can see that the input starts off as white, which means it's a neutral input, can take a number of different types of input, and let's disconnect these. The output also starts as white, but as soon as we connect this float here, we can see that the output turns into a float as well. And that's true here. So a node like the add node takes a variety of different inputs, and the output will depend on the inputs. Note that if we try and add, let's create another constant, press P to bring up parameter window, and I'm going to turn this into a 3-float vector. If I then try and add that, I get a dotted line, and a dotted line means that this isn't really working in this context. It's converting this vector into a float in order to make it work with this node. And the order in which you attach things is obviously important. In the add node it's not important because of the order of addition, but because if we make our vector the first node and take this out, then it now works. The reason it works is because a vector plus a constant means that you add the constant value to each component of the vector. Similarly, if we take a multiply node, we can multiply two floats like so, or we can multiply a vector by a float, and that still works. However, if we start with a float and then multiply the float and then the vector is the second input, we get this dotted line indicating that this vector is being converted into a float before going into the multiply node, which is not necessarily what you want. In some cases the type of the output is not determined by the type of the inputs. Let me lay down a random node, and this just creates a random number based on a position vector. So let's feed in a vector, and we can see that the output here is a float. What happens if I wanted to output a random color or a random vector with 3 components? If I bring up the parameter editor for this, we see that we've got at the top here something called the signature, which says 3D vector input and 1D output. And in this case, that reflects what we've got here. We've got a 3D vector input, we're just getting a single float out. I can, however, select from any one of these options, and I can select 3D vector input, 3D vector out, or 3D color out even. And now we can see that we've got a color. Let's get rid of that. Another aspect of VOP nodes is that you don't necessarily need to connect all the inputs. Let's lay down a lighting model node, and we can see that it has a great many inputs. It's got a number of vectors and some float inputs. Now, in fact, you can examine the inputs as part of a parameter editor. If I hit P, we can see that we've got a lot of these inputs: the ambient color, the diffuse color, the specular color, U roughness, V roughness, face forward, tangent style, and so on, available as parameters. And if I connect, for example, a vector here into our ambient, we can see that this becomes grayed out, so that we can no longer set it using the parameter editor. So we can have a combination here of nodes which are connected into these inputs and nodes where or inputs where we're setting the value using the parameter editor. But we can also see that some of these inputs, NN and NI for example, are not reflected here in the parameter editor, but they are inputs. And this is because they're quantities which relate to generally to the global variables here, and we don't in fact often need to connect things here. We need to look at the help card to determine if we need to connect things. For some nodes, things like this will default to the global variable. Let's have a look at the help node for lighting. And we can see if we scroll down that the inputs for normal and incident, and this is N and I, should be normalized if explicitly connected, which is why we've got a little n in front. If either is not connected, the global variable by the same name is used instead. In other words, in general you won't need to connect these, although it's often good practice to do so by connecting them here to the global variables with the same name. So in addition to having nodes which can take multiple types of input, like for example the add node, we can take something which has a vector value, here this is a 3 float vector, and connect it quite safely to something which is a color. And you can see that this solid 9 means this works. And I can convert this to any of the 3 value types. I can convert it to a vector, I can convert it to a point, I can convert it to a direction, I can convert it to a color. All of these still work. So there's a certain amount of automatic conversion happens. You can convert any 3 valued type into another 3 valued type. And similarly you can connect a float value to any float input or to any integer input. Finally, a word about constants and parameters. Let's bring up a lighting node again as a good model. I can create constants for the inputs here. So let's do that. We middle click on an input and we can say create constant. And a constant is a way of inputting a value which we can set here. We can change this input value without creating a parameter and without editing this in the parameter editor here. You can also use constants as variables, and although they're called constants, you can in effect change their values as they pass through a network. And that's useful, for example, in things like for loops, which we're not going to actually cover in this tutorial. Very similar is a parameter. Let me create a parameter. Again, middle clicking and selecting create parameter. And let's bring up the parameter editor for this parameter node. And we can see we've got the defaults as for a constant, but we've also got a parameter label and various inputs here. Now, a parameter by default, as we set it up here, is something that will appear on the top level parameter editor of the material. In order for it to appear, I need to promote material parameters, and then when I hit P to bring up a parameter editor, we see that our ambient color parameter is available. So if you want to have parameters which you can change at the top level in the material, you need to create parameter nodes. In some circumstances, you'll want to make these nodes invisible. So what's the difference between a constant and an invisible parameter node? Well, the answer is that if we are using this to shade geometry, then the parameter node can pick up values from the geometry itself. For example, I could create a parameter node and make it a color and call it CD, and this would pick up color attributes from the points in our geometry. If we make it invisible, it'll do that without itself appearing in the parameter editor for the material. A final use of parameter nodes is to export values from your shader, and you can do this by creating a parameter node and setting the export value here to always. At this point you'll see we get an input in our parameter node, which is of color type, and if we can connect something to it, then we have an exported parameter with this name. And we can use that when it comes to creating extra image planes in Mantra, and we can effectively create an image plane which has a value of this variable for every pixel in the scene, and later on I'll demonstrate how to do that. So that's a brief introduction to nodes in the Vex Builder context. In other words, an introduction to VOP nodes. So let's go ahead and start constructing our shader. And the first thing I need to do is create a material. So I'll lay down a material, and we're going to call this wood planks. If I dive inside, I've got a sub-output node. And a material is a way of combining different types of shaders, in particular surface shaders and displacement shaders. And today we're just going to look at a surface shader, and we're going to build a surface shader using a VOP network. So what we need is a Mantra surface and then a VOP Vex surface shop. And then we connect that into the sub-output. That ensures that our material will be rendered using this surface shader. And then I can dive inside, and let's enlarge this, and I get an output node, which is going to be where we put the final result of our shader calculations, and I get a global variables node. And let's have a look at the global variables node in a bit more detail. So the shader is operating on a single micro polygon, and you get a number of variables, as we mentioned, which give you information about that micro polygon. To start with, you have the position information. This gives you the position of one corner of the micro polygon, and then you get two vectors, dp ds and dp dt, which offsets from the position of that corner to the other two corners that are adjacent. Then you get another vector, which is the normal, n, which points away from the surface. You then get a vector which points from the camera to your micropolygon, and it's important to remember the direction of that vector. It's from the camera to the micropolygon, not the other way around. And finally, when you're in an illuminance loop, when you're calculating lighting, you get a vector L, which is the vector from the position of the light which you are calculating to the micropolygon. So the first thing I'm going to do is lay down a texture node. The texture node is something that allows you to apply an image, in other words a texture image, to your object. And I'm going to create some parameters that I want to be visible in our material for this texture node. And I do that by middle-clicking on these inputs here, the ones that I want to make into parameters. Alternatively, I can right-click on the node and select Create Input Parameters. But in this case, I don't want input parameters for all of these inputs. I just want it for some. So I'm going to do it one by one. So I middle-click on the node and select Create Parameter. Now, I've selected here the most commonly used parameters for this type of node. These parameters at the end here are slightly technical, and you don't normally need to adjust them. And this group of parameters here are the inputs which control how the texture is positioned on the object. And those need to be derived from the object itself rather than from the parameters of the material. Now, by convention in Houdini, parameters are coloured yellow, so I'm going to hit C to bring up a colour swatch. I'm going to select all our parameters and I'm going to colour them a light yellow, and hit C to get rid of the colour swatch again. And I'm going to pause the video and rearrange the parameters so that they're a bit neater. Now, I need to provide values for these inputs here, S and T. S and T are the texture coordinates. Texture coordinates are a way of applying a texture, which is essentially a 2D image, to an object which is, of course, three-dimensional. And you do this by applying something called texture coordinates to points in your object, and then using those to position your texture. In fact, all of the primitive types in Houdini have some kind of texture coordinates already defined. And that's what you get if you use these variables here in the global variables node. So let's have a look at what happens when we connect S and T into S and T here. And I'm going to take the color output of our texture and connect it to the CF output here. Just a quick word on what these other outputs mean here. CF is the color, and that's a vector, has 3 components. OF is the opacity, that also has 3 components. AF is the alpha, that's a single float value, and I'll comment later on the difference between the opacity and the alpha. N is the surface normal, and F is a special variable that's used when constructing PBR shaders, and we'll also talk about that a little later on. If I want to have a look at the parameters of a node, I can just select it and hit P to bring up a parameter editor. And for example, for these nodes here, which represent a parameter that's going to be visible at the material level, we have a number of options. For example, we can choose the label of the parameter and we can choose its default value. The output node has a special type of parameter editor. What we've got here is a list of all of the parameters that we've defined, these nodes here. And this allows us to rearrange the nodes, which I can do either using these arrows or I can click and drag. It also allows us to group them into tabs. And we can do this by selecting the nodes. I've shift selected there, so I've selected all of them, and clicking on one of these arrows. And this produces a group, as you can see, enclosed in curly braces. And we can rename our group. I'm going to call it, I just click on that, and then I can type in a new name. I'm going to call it texture. And then let's go up a level and have a look and see what the parameters are on our box surface. Well, we can see we've got a tab called texture, and then we've got our parameters with their default values. If I go up again and have a look at our material, however, we don't seem to have any parameters. And that's because every time you change the parameters here in the shader, you need to promote them to the material level, and you do that by right-clicking your material and selecting Promote Material Parameters. And there we have our material parameters. So let's have a look and see what this looks like when we render it. So there's our grid. We can select the Mantra renderer and have a look. And what we're getting are lots of copies of the mandrel picture, which is the default texture map. And that's not necessarily what we want. What we want is a single large mandrel across this entire surface. Well, let's see if we can fix that. And the first step is to lay down some texture coordinates for our grid. And we can do that using the UV project node. And since it's a polygonal grid, we want to project onto the vertices of the grid, and orthographic is fine because it's flat, so I'm going to initialize that. Let's try another render. And exactly the same thing is happening. So obviously that wasn't sufficient to address the problem. And the reason is that when we used the S and T coordinates here from the global variables, what we're getting are the natural texture coordinates of that particular primitive type. And in the case of polygons, they have natural texture coordinates which vary from 0 to 1 across each face. So having a look at our grid, we can see that it has, let's go up, it has all of these different faces. It's got 100 different faces, 10 by 10. So each of those has got its own set of texture coordinates and will have its own copy of the mandrel image. And that always happens when you use these S and T values from the global variables. And that's fine, in fact, if you're shading a NURBS surface, because that has sensible S and T values, and you can probably simply feed them in to your texture map. But it won't work for polygons. We need to try and rely on those texture coordinates that we've just projected onto the grid. And there are two ways of bringing them into your shader. One is to use the UV coords node, and that's the best way for the example we're doing at the moment. Another way is to use the shading layer parameter, but using shading layers and multiple UV coordinates is beyond the scope of this tutorial, so I'm going to delete that and use UV coords. Now, UV coords has three outputs. You can either output your UV coords as a vector, UVW, or you can use these S and T coordinates, each of which is an individual float value. Now the S and T coordinates here are not the same as the S and T values here. If you take S and T from here, if you've projected texture coordinates onto your object, then these will reflect those texture coordinates. If you haven't, these will reflect the natural texture coordinates of the primitive that you're shading. So let's connect the S and T values. Let's move this up here. And let's minimize this and try rendering again. And now we get a single big mandrill image. It's worth saying something about the distinction between using textures as the basis of your shaders and using procedural shaders. Textures do have an advantage, and that's to do with aliasing. We can have a look at this image here, which is the result of a surface shaded with a poorly written procedural shader that's producing these checks. And as you can see towards the back of the image, there really is a lot of artifact. In other words, there's a lot of aliasing on this image. And if we compare this now to a check shader which is applying a texture map to the surface with the checks on it, we can see that the aliasing is much less pronounced. And that's because Houdini, and indeed any renderer, is able to do pre-filtering on the texture, which makes it fast and easy to alias it. Image-based textures do have a disadvantage, however. They're made up of a limited number of pixels. So there's a danger that if the camera gets too close to your surface, you'll be able to see the pixel level detail, or the surface will start to look very bland because there isn't enough variation as you get close. Procedural-based textures are able to have almost infinite levels of detail, and so can look good even when the camera is very close to the object. In practice, it's often best to combine image-based textures and procedural textures, so that you have the advantages of an image-based texture while adding complexity and variation using a procedural part of the shader. And that's exactly what we're going to do in this example.